Welcome, everyone, to today's conversation. We're going to be focusing today on some of the deep and perplexing issues, mysteries, achievements as well of modern cosmology. We'll try to come to grips with what many see as the most pressing current challenge facing cosmological theory, which is known as the Hubble tension. And then we'll also spend some time talking about the remarkable discovery that we are still fully, deeply grappling with, this discovery of dark energy suffusing the cosmos. And the person that we're speaking with today is a leader in all of these undertakings. It's Alex Filippenko, who is the Richard and Rhoda Goldman Distinguished Professor in the Physical Sciences at the University of California, Berkeley. He is the past winner of the Breakthrough Prize in Fundamental Physics. He's also won the most prestigious teaching award at UC Berkeley and been voted the best professor on campus a record 9 times, which is absolutely amazing and wonderful. He joins us now from his office in Berkeley, California. Hey, Alex, how you doing?
Hey, pretty well, Brian. It's such a pleasure to be here. And in fact, for my introductory astronomy students, I held a 3.5 hour session late last night on cosmology and the early universe and dark energy and things like that. And they were so jazzed that I would be on your program because they love it and the World Science Festival and all that. So I'm very honored and privileged to have been asked by you to join you this morning.
Well, thank you for those kind words. It's always great to hear that the younger students are watching these programs. After all, look, they're meant for everybody, but when you can reach the next generation and inspire them, as you clearly have been doing, if we're helping in that regard as well, it's gratifying to hear.
Yeah, thanks. Well, you too, with your books and all of your public outreach, one of the joys of science, I think, for both of us is bringing it to the general public and showing them that it's such an interesting and noble profession and such an interesting subject, right? That we can actually figure out things about the universe and our place in it and the origin of the elements of which we are made and things like that. It's just fascinating. And a lot of the students who take my course, it being a general ed course, took it only because they have to take some sort of a science class and they heard it's a good one, but they weren't necessarily interested in science to begin with. And then by the end of the semester, a lot of them ask me, well, how can they learn more? And I think that's the ultimate achievement, to have presented the subject in such a way that non-science students feel compelled to learn more. And I think both of us like doing that.
Yeah, no, it's absolutely gratifying when that's the outcome. And, it just brings to mind one question before we get into the details of things like the Hubble tension and dark energy, as I mentioned at the outset. Richard Feynman, I think, once famously said that the single most important lesson from science is this idea that we are all made of atoms. You made reference a
Yeah.
moment ago to the stuff of which we're made of, and we've learned that forged in the interior of supernovas,
Hmm.
exploding,
Yeah.
spewing out. So it's a deep insight that we're all made of the same stuff, forged in the same place. But if you were to come up with the single most important lesson that you'd want, say, your students in that class or people that watch these programs, what would you say is the most important lesson of science?
Well, I think in Feynman's case, you're right. He was searching for a single sentence that would convey the most information in the fewest words. And I think he was focusing mostly on just that matter is made out of atoms, which at some level are indivisible in terms of, carbon being different from oxygen and all that. Of course, there are protons and neutrons and electrons and all that. But he didn't focus on the origin of the elements, the heavy elements of which we are made. And so I would put uh, this addendum to what he said, and it's sort of what you said, that the carbon in our cells, the oxygen that we breathe and which is in water, the calcium in our bones, the iron in our red blood cells, the phosphorus in our DNA, all of the elements heavier than helium, or technically lithium, but there's not much lithium within us, they were forged in stars, deep in the cores of stars through nuclear reactions. Indeed, this is what produces the energy that the stars emit. And then some of those stars explode as supernovae and liberate those elements into the space between the stars and generate additional heavy ones during the explosions. And then those gases form new stars and they go through birth and element generation and death. And after many generations of this stellar birth and death, you get clouds that have a sufficient quantity of these heavy elements that rocky Earth-like planets can form. And at least on one of them, Earth, life did form and it evolved, and here we are. So going back to Carl Sagan, he so eloquently said, we are made of stardust or star stuff. And that's just such an amazing story. We're not just in the universe, we're an integral part of the universe linked to stars billions of years ago that generated these elements, and some of the stars exploded. And aren't we lucky that all of this happened?
Yeah.
So I think that's just an amazing story of creation, in a
Yeah.
sense, and of our fundamental origins.
Yeah. Sometimes I like to think about if somehow the atoms in our bodies were tagged with their place of origin.
Yeah,
It'd be sort of this amazing story, it'd be like 23 and Me, but at the level of, the lineage from the atomic furnaces through which these atomic structures were forged, the atom
yeah,
over here in that star
right.
and that the atom over, that sort of
Yeah,
capacity,
absolutely. The life history of a particular atom,
yeah, yeah, kind of amazing. So you mentioned supernovae, and that's going to be part of our conversation, of course, because those exploding stars have played a different but vital role in the work that you and your colleagues have undertaken over the course of decades. But I wanted to start first with this issue that has certainly been heralded by some as this critical juncture for cosmology, this Hubble tension, these two different ways of measuring the expansion rate of the universe. But we've had other people on this program, and I've had many conversations where some scientists are just sort of shrugging their shoulders and saying, it's all going to work out. It's all going to go away. The measurements are kind of at least overlapping a little bit now from these two approaches. And so 5 or less years from now, we won't even hear about the Hubble tension any longer, while others are saying, I don't know, this is going to change everything. So to get there, if you could just sort of lay out what the tension is, and then maybe through our conversation, we can backtrack and lay out the two approaches a little bit more detail, just to give people a
sure.
sense of it.
Yeah, I'm happy to do
Yeah.
that. Yeah, so fundamentally the tension is the following. There are various ways of measuring the rate at which the universe is currently expanding. Okay, it's a number called the Hubble constant, but better to call it the Hubble parameter because it actually changes with time. It's just that at a given time, it's thought to be constant throughout the universe on average, but it changes with time. Anyway, we can measure what it is now. And then there are ways of predicting what it should be based on observations of the early universe, the infant universe, when it was only about 380,000 years old. And there are these radio measurements really at microwave energies or wavelengths. And they take a snapshot of the universe when it was just an infant. And there are these little freckles, and we can talk about them some more. But basically, through those measurements, and then what's called the standard model of cosmology, which has 70% this repulsive dark energy that we can talk about now, which is causing, we think, the accelerated expansion of the universe, and then 30% normal gravitating matter. You take that combination of stuff and you kind of project forward nearly 14 billion years, and you can predict what the current expansion rate should be if the early time measurements are correct and if our standard model is correct. And what you get is a discrepancy of between 5 and 10%, something like 8%, 9%, between the currently measured rate and the predicted rate. The measured rate is faster than the predicted rate, and the predicted rate takes into account the known acceleration of the universe that we've known about for a quarter of a century now. And, Adam Rees has led the team that has made the most accurate and we think the most precise measurements of the current Hubble constant. And I've been privileged to be part of that team. And we've been doing this work for 20 years. And over the years, the discrepancy has become more and more real in a sense. You can ask how much do the various measurements and predictions overlap, and they've been overlapping less and less and less as we've improved the accuracy and precision, mostly the precision of our measurements. And now they overlap so little that there's only a one in a few million chance of a statistical fluke where what we've measured really is the same number because they overlap a tiny bit, and the universe isn't trying to tell us anything new and interesting. But there's only a chance in a few million of that. It has reached what's called the 5 sigma level, 5 standard deviations. And that's the gold standard, at least in high energy particle physics. When the Higgs particle was announced 12 years ago, the two teams that were doing that with the Large Hadron Collider actually combined their results. They were each, I think, at 4.9 sigma, and they combined them to make the magical 5 sigma, and they proclaimed a discovery. Well, we've reached a 5 sigma tension now, and so we think it's real. And we can talk more about different ways of making the current measurements and stuff. But basically, I think it's a real discrepancy, and the universe is trying to tell us something is missing in the standard model or slightly incorrect, because I think our current measurements are correct, and I have no reason to think that my colleagues doing the microwave background measurements have done something wrong. There's something wrong in the assumptions, either in the going from the infant picture to now, or something in the early universe that affected the assumptions going on when interpreting the infant picture of the universe.
So can we drill down on that now a little bit further and maybe start with the measurements that you and Adam Rees and your colleagues have been doing, which are the current measurements, if you will,
Yeah,
of the expansion rate, as opposed to the expansion rate then extrapolated from the early universe to today.
right.
And I gather one of the main hurdles in measuring the expansion rate of the universe is knowing how far away an object is, right? We're pretty good at determining how fast an object is moving away, by the redshift in the spectral lines that we receive in our telescopes. But measuring distances has been the big headache over the course of modern cosmology. So how do you go about undertaking those measurements?
Yeah. So you're absolutely right that the speed with which they're moving away from us is a straightforward measurement. It's a little bit akin to the Doppler effect that people hear when a siren is going away from them and the pitch sounds low, or when the siren is coming toward them and the pitch sounds high. So we can measure these shifts in the wavelength. In the case of distant galaxies, they're actually caused by an expansion of space itself, we think, rather than galaxies moving through some pre-existing space. But whatever, at low speeds, you can use the Doppler formula and all that. The distances are the big bugaboo, right? We need to get distances that are independent of this Hubble or Hubble-Lemaitre law that tells us that the speed is proportional to the distance. There, you kind of have to know the Hubble constant, that constant of proportionality. So you need a distance that's independent of the Hubble-Lemaitre law. So what we generally try to do is find a star whose intrinsic power, whose oomph, whose luminosity we know. It's a little bit like a headlight of a car of known distance, 2 meters away. And you say, whoa, that's a pretty bright headlight, but you know that it's 2 meters away. So that allows your brain to calibrate how powerful it really is. And then you find a similar type of star in a distant galaxy or a similar headlight on the road, and you look at how faint it appears to be, and your brain kind of automatically, in the case of a car, determines its distance. You're actually using what's called the inverse square law of light, but no big deal. We look at enough car headlights and we get an intuitive, almost instinctive feel for how far away the car is. And I like to joke with my students that if you're not very good at doing this at night, you shouldn't be driving at night, okay? So we find a type of star whose properties we know, and some of whose members are close enough that there's a way of determining their distances And by measuring how bright they appear to be, that then allows us to determine how powerful they are. And then we find them in the more distant galaxies and determine the distances of those galaxies. But there's no single type of star that is visible at the vast distances of billions of light years. And a light year is the distance light travels in a year. It's about 6 million miles. Okay. There's no single type of star that's visible, at vast distances, but also whose distance is directly measurable nearby. Okay. So we need some intermediate type of stars that give us the distances to at least some galaxies, and we can measure their distances of these stars more or less directly, and then find a type of star in the galaxy whose distance you've figured out using this intermediate star, and calibrate that candle, so to speak, and then use it out to billions of light years. So to just make this very concrete, for relatively nearby galaxies, we use a type of star known as a Cepheid variable. And these are stars that are hundreds and up to thousands of times more luminous than the sun, so they can be seen out to distances of tens of millions of light years. And they're not all exactly the same, but they vary in brightness. And the ones that are on average more powerful are also the ones that on average have a longer period of oscillation. So they are variable stars, but we can find them in our own galaxy and we can find them in nearby galaxies. And now with satellites like Gaia that can measure slight shifts in the positions of the stars in our own galaxy, depending on where we are in our orbit around the sun. It's a little bit like measuring the shift in your finger when you close one eye and another. It's called parallax. With Gaia, we've measured the parallaxes, thus the distances of the Cepheid variables in our own galaxy. We measure their brightness. That determines their oomph, their power, their luminosity. Now use those same kinds of stars in galaxies that are tens of millions of light years away, measure their distances. And in those galaxies, we then find exploding stars of a particular type, the type 1a, and we can get into that later if you want, but they're more or less standard and they're very powerful. They're billions of solar oomphs, solar luminosities. And so if we then measure their distances and their peak brightness, that allows us to calibrate how powerful they really are at their peak. Then we can go out to galaxies that are hundreds of millions of light years or even billions of light years away, find type 1a supernovae within them, and thus determine the distances of those galaxies. So you see, it's called a distance ladder, and it has various rungs. And like any ladder or any chain, it's only as strong as its weakest link. And so you have to make sure you understand where you could be going wrong in each of those steps.
So one of the questions that immediately comes to mind is you needed to find, say, some Cepheid variable and gain a real deep understanding of how its brightness changing over time and its overall brightness were correlated. The brighter they are,
Yeah.
the longer the period of oscillations of the brightness. And then you needed to find in distant galaxies versions of those same stars. Is that step something that ever gives one pause, or are you pretty confident that you are able to find the same kind of star and it's not somehow in some way that we don't fully understand different?
Yeah. So that's a really good question. It's been over a century that these stars were first identified and studied in detail, and the so-called period luminosity relationship was found by Henrietta Leavitt, who observed satellite galaxies of our own Milky Way. They're called the Magellanic Clouds, or the Clouds of Magellan. And these are stars that are all more or less at the same distance from us. So the distance effect wasn't then a variable. They're all at the same distance. And Henrietta Leavitt found that the ones that appear brighter have the longer period, and the ones that appear fainter on average have the shorter period. And so she was able to then realize that those that have a longer period are intrinsically more powerful. Now, you do have to be careful because there are different types of Cepheids. And Edwin Hubble, for example, didn't realize that a century ago when he first determined that the Andromeda Nebula is actually a galaxy, an island universe, if you will, outside our Milky Way. And he got somewhat the wrong distance, and then, distances to other galaxies he got a bit wrong. And so his initial value for the Hubble constant was in fact quite wrong. So you have to realize that there are different types of Cepheid variables, and you have to be careful there. And you have to make a small correction for the heavy element abundance of the galaxies in which they reside. So there's a slight dependence on what's called the metallicity. The metallicity is just a fancy term for what is the fraction of the gases that are elements heavier than helium. So we make a correction for that. And that's where my main role in the project came. I would make measurements with one of the Keck telescopes in Hawaii of the chemical composition, essentially, of the stars and the gas in those galaxies. So we make that correction. And then you have to make a correction for the possibility that there's dust or fog in the way that's systematically dimming the light of the Cepheids. But we think we have a way of doing that. But when you do all that, we feel that we have a pretty good calibration. And the Cepheids behave in the same way. It looks like a duck, it quacks like a duck, it walks like a duck, smells like a duck. It's probably a duck, but you need to make as many different measurements of the Cepheid variables and later of the type 1a supernovae as possible to validate that you really are looking at the same kinds of light bulbs or headlights. So that is a very important step. But we've been studying the Cepheids in some detail. And although 20 years ago, or even 10 years ago, we didn't have any direct distances to any of the ones in our own galaxy, because they're pretty rare stars. And so there are very few that are nearby enough to use these parallax measurements. But now with these satellites, first Hipparcos and now Gaia, which measures these parallaxes to billions of stars, some of which are Cepheids, we've really nailed that rung of the distance ladder. And we can then find exactly the same kinds of Cepheids in these galaxies that host type 1a supernovae. So we're pretty confident about the Cepheids.
I see.
Yeah.
And so then the rungs on the ladder, then, just to quick summarize, if things are sufficiently close, you just use parallax to determine how far away
this
you are.
this
That
is the
usual
best example.
jumping back and forth of your
That's
finger.
actually why you have two eyes, or one of the reasons you have two eyes is that it
Depth
gives you two different perspectives. It gives you the depth perception.
Yeah, precisely. Then beyond that, the Cepheids are a tool that now allows you to go further out. And then the type 1a supernovae, based on the detailed observations of their brightness when they explode and how quickly that comes down in brightness, gives you a third rung on that ladder. And so how far out then would these three rungs on the ladder typically take you?
Yeah, so, for the discovery of the accelerating expansion of the universe, we needed to look back in time and thus to distances of 3, 4, 5, even 6 billion light years. Okay, and so we did that with supernovae, and we could trace the expansion history of the universe. We can discuss that later if you wish. But for the Hubble constant, you actually don't want to look back billions of light years because you will be looking back to a time when the universe was expanding at a different rate. It wouldn't be the rate now.
Yeah.
So you want to look to only a few 100 million light years. And you might think, well, that's still looking back in time. That's a long way back in time. But compared with 14 billion, 200 million or 300 million is not that much. That's essentially a measurement now. But we can't see the Cepheids out at a few 100 million light years, but we can see the type 1a supernovae really easily, okay? So what you want to do is have the intermediate distance galaxies where you can see both the type 1a supernovae and the Cepheids. And those have typically been sort of from 20 to 50 or 60 million light years away. You don't want to be much closer than about 10 million light years, because at distances below that, galaxies and galaxy clusters tug on one another and cause motions that significantly affect the derived speed of expansion, because then the speed that you measure from these various features in the spectra or whatever you're doing, they they are augmented by these so-called peculiar motions that are caused by galaxies pulling on one another. So you're not getting the expansion rate of the universe. But if you go beyond 100 million light years, then you're not seeing the Cepheid variables. So somewhere between 10 and 100, and the sweet spot is sort of between 20 and 60, something like that. You can measure type 1a supernovae and the Cepheid variables. And of course, we'd like to measure as many galaxies as possible with the Cepheid variables. But when you go much beyond 60 million light years, it starts to be hard to see the Cepheid variables, and they become crowded with stars, random stars in those galaxies next to them. So you don't know whether you're measuring one star, okay? That was indeed a potential criticism of our work a few years ago, but now with the James Webb, we can see that we really did measure single Cepheid variables that are not crowded. But we'd like to go as far out as possible because, of course, that increases the odds that we have some type 1a supernovae as well. So now our sample has 42 galaxies with type 1a supernovae and Cepheids. And I like that number because you may be, of course, familiar with the fact that 42 is the answer to the question of life, the universe, and everything, at least according to Douglas Adams, right?
Sure.
So I liked it that we stopped at 42, and we published this paper 2 years ago now, where we reached this 5 standard deviation level, hence a real discovery.
And I think we may have an image, although I'm not completely certain, but I think we have an image of some of those.
These are the ones that have multicolor Hubble Space Telescope images. And so you can combine them to give sort of a true picture of those galaxies. And you can see they're spiral galaxies, like the galaxy that we find ourselves in, the Milky Way galaxy. And those are precisely the kinds of galaxies that can have Cepheid variables, because Cepheid variables come from evolved but reasonably massive stars. And in the other main type of galaxy, the so-called elliptical galaxy, their star formation ceased by and large a long time ago. And the massive stars, somewhat paradoxically, you might think, live shorter lives than the less massive stars because they burn, in a nuclear sense, their available fuel more quickly. So they burn out. And so there aren't any Cepheid variables in the elliptical galaxies, but there are Cepheid variables in these spiral galaxies that have a population of reasonably young, massive, but evolved stars that turn into Cepheids. And these are 36 of our 42, and these are also hosts to at least one type 1a supernova. So these are the golden objects. We love these galaxies.
And to find the Cepheid variables, I remember, you mentioned Henrietta Swan Leavitt. As I recall, she was taking, 2 photographic plates of the same portion of the sky, sort of, subtracting one from the other, sort of overlaying them, sort of finding, a star that appeared bright in one, but less bright or not bright at all in the other. Do you play a similar game to actually find these Cepheid variables?
Yeah, you can digitally subtract one image from another, and a star that's blinking will appear. The Cepheid variable is there and is visible in the Hubble images, which are exquisite, even at minimum brightness. So it never completely disappears. But if you subtract the image when it was fainter from the image when it was brighter, you can see it blinking. For the supernovae, we use this digital subtraction, and there, in the subtracted so-called difference image, we see an object that simply wasn't visible at all in the image before the star exploded. So the subtraction technique is even more important for the supernovae, because really looking at the Hubble images, just even by eye, you can kind of see which ones are variable. But it's easier to do if you do the digital subtraction, because then it blinks.
And how frequent do you have a hit? I mean, do you sit there waiting, and say, "Oh, subtraction is fine," or is it something that fairly regular basis on the data that you observe, you find things of that sort?
Oh yeah. These relatively nearby, well-resolved galaxies, that means we can see lots of individual stars in the exquisite Hubble images. They have dozens to hundreds of Cepheid variables. So in a comparison of any two images separated in time, some of them will be blinking high and some will be at their low state, but you'll find a bunch of these things. And we actually have to take more than two images. We take many images, like a dozen images, because you need to find the period over which the brightness of the Cepheid is varying, because that then correlates with the true oomph, the power
Intrinsic.
or average luminosity of the Cepheid variable. And
Yeah.
there are techniques where we can improve uh, the well, we can get the necessary observations with the fewest Hubble pointings, because of course this all takes time, and Hubble time is very precious commodity. Lots of people want to use it. So you don't want to just take hundreds of images if you don't need hundreds of images, but you might need a couple of dozen images or a dozen images at different stages of the light curve in order to nail down what the actual
Yeah.
period of the Cepheid variable is.
Right.
And we also want to use as wide a span of wavelengths as possible, because then you can see an object that's fainter and more distant than if you're just looking at blue light or red light. If you're looking at the whole thing, then you can see more of the light. And so over the years, we've been perfecting not only the cadence, the time intervals over which we do these images, but also we've been gradually expanding the wavelength range over which we can do these measurements, because with the servicing missions on Hubble, the instruments have gotten better and better. They've become more sensitive and they span more of the optical wavelength range. And so with time, over the 2 decades that we've been doing this project, we've been able to sample progressively more distant galaxies, thus increasing the probability that some of them have type 1a supernovae, because the type 1a supernovae are quite rare, once every 500 years maybe for a galaxy like the Milky Way.
Right, right.
Yeah.
And so if we can bring up on, this cosmic distance ladder
Yeah,
summary image, so
sure.
we can sort of keep track of where we are at the moment. So with all the wonderful data that you just described in terms of the Cepheids and the type 1a supernovae and so forth, we have this, beautiful summary here where you now have this technique of measuring distances, out to hundreds of millions of light, even further if you wanted. But for this project in particular, measuring the expansion rate today, together with spectra, how quickly things are moving away, distances, how far they are. So this is your approach to measuring this critical parameter, the Hubble parameter. And what then do you find when you put
Yeah.
it all together?
Yeah, this is a great diagram, because it shows at the left there that Earth at different places in its orbit has a different line of sight for a relatively nearby star against the background of the so-called fixed distance stars that aren't moving very much in angle. And we can measure that little angular shift very well with these satellites now. So we got direct distances to the Cepheids, so we know how powerful they are. We then find them in the galaxies of order, say, 50 million light years. And those are the galaxies in which we've also found type 1a supernovae. So we measure how powerful the type 1a supernova is by looking at its peak brightness and knowing its distance. And then we find the type 1a supernovae in the more distant galaxies. And those are the ones that are sufficiently distant that their speeds of recession are caused mostly by the expansion of the universe, not by galaxies tugging on each other. And there's some steps that need to be taken to standardize the type 1a supernovae. We can talk about that as well if you wish. It's a little bit like recognizing there are different types of Cepheids and taking care of the fact that their brightnesses do depend a little bit on the chemical composition and stuff. So there are some tricks we need to play with the type 1a supernovae. But having said that, what we find is the current expansion rate of the universe. And the number we find in some weird units is 73. Now, those units are kilometers per second. Okay, so that's a speed per megaparsec. That's the part that's a bit confusing to a lot of people. First of all, a parsec is just a fancy word for 3¼ light years. All right, and mega is a million. So it's a convenient unit for astronomers, but it's kilometers per second per megaparsec. And the point is that there's no single expansion speed for the universe. It depends on distance because every bit of space expands. And so the more distant a galaxy, the greater is the amount of space. And so the more stretching there will be. And I actually have a little demo here. I have these ping pong balls
Beautiful.
on a rubber hose. And let's say we're on this orange one right here. And I stretch it, and in a given amount of time, then the nearby galaxies moved away from the orange one by a relatively small amount, so their speed was small. But if I go to one of these more distant ones, there was more rubber hose between the one I'm on and the more distant ones than between the one I'm on and the nearby ones. And every bit of the hose stretched. So in a given amount of time, the more distant ones move away more than the more nearby ones. And so that's why it's a speed per unit of distance, okay?
Yep.
But anyway, we measure 73 in those funny units.
And so that
And
means,
yeah.
and by the way, I'm going to steal that idea from my class.
Oh, I may have
I do
stole.
it all with animation. I do it all with animation, but I think that's, a more convincing version to actually see it done for real in
Yeah, I
terms of
think I stole it early in my career by watching some other really great lecturer use it.
right.
So I
That's
did
what we
not
all do.
think up that particular analogy,
Right. No, it's very nice.
though I would
But
like to take credit.
so the point is, at a megaparsec of separation, two galaxies would be speeding apart at 73 kilometers per second.
Exactly. Right.
Um,
And at 2 megaparsecs, it would be
twice that.
twice that, 146. But I want to emphasize that at only 1 megaparsec, 3¼ million light years, that's not a big enough distance over which to see unambiguously the expansion of the universe, because clusters of galaxies, which are gravitationally bound, are of order a megaparsec. And you really need to go out to 10 million or more light years, in other words, 3 or 4 megaparsecs or beyond, to start seeing the expansion of the universe. And I would say you want to go beyond 10 megaparsecs for you to start being dominated by the expansion of the universe rather than by these tugging motions of galaxies for each other, or the motions induced within clusters of galaxies because all the galaxies are sort of orbiting one another.
Yeah, same reason why we can't measure the expansion of space by looking at our own bodies.
Yeah.
We're
We're
held
held together
together.
by electromagnetic forces that are much
Yeah.
bigger than the tendency of otherwise empty space to expand. Right.
Yeah. And so you have this number, 73 kilometers per second per megaparsec, and that's what in our preamble discussion you would call the expansion rate today, the direct measurement. If we could turn now to the second approach,
Yeah.
where we're going to find some tension, which is, as you described eloquently early on, taking measurements of the early universe and then using our theoretical models to extrapolate to what the expansion rate would be today. Can you give a sense of how people actually go about that prong of the
Yeah.
measurement apparatus?
If you don't mind, Brian, I'll first just touch quickly on an issue that I mentioned earlier, but that I think will interest you because you specifically asked whether we're confident in the Cepheid measurements. Okay. And I said, I think we are. The other thing, though, that we need to be confident of is the type 1a supernova part of the distance ladder. And there I had mentioned that we have to calibrate them, because it turns out that although they all explode in about the same way, they come from a type of star known as a white dwarf, which our sun will become in about 7 or 8 billion years. Um, it'll be about half the mass of the sun compressed into a volume the size of Earth. So it's very, very dense. It's a type of matter, as you know, called degenerate matter by quantum physicists, not because it's morally reprehensible or anything like that, but that's just the term we give to it. But anyway, our own sun will be a solitary white dwarf and it won't explode. But a white dwarf in a binary system can steal material in some circumstances from the other star, grow in mass, and reach a critical mass, at which point an uncontrolled thermonuclear reaction destroys the whole star and makes it a couple of billion times as powerful as the sun. So we think that that occurs in about the same way each time. And indeed, for the type 1a supernovae in nearby galaxies, to a first approximation, we can confirm that they're all about the same. But the devil is in the details. And when you're looking at the expansion of the universe, the details are important. And we find that some are more luminous than average and some are less luminous at peak than average. So they're not exactly standard. In fact, I don't quite like the term standard candle that many astronomers use, but they're standardizable. It's like they're not all 100-watt light bulbs. Some are 90, some are 107.5 or whatever. But there's a way of reading the label on the type 1a supernova light bulb, and that's the following. We've empirically, observationally found that the ones that are more luminous at peak also rise and decline in brightness more slowly than average, and then the ones that are less luminous at peak rise and decline more quickly than average. So it's a little bit like a Cepheid type relationship. And it was discovered by Mark Phillips in 1993, so about 30 years ago. And that's what made type 1a supernovae into a precision cosmological distance indicator. The fact that we can read the label on the light bulb, and there are other details that, you know, we could go into, but that's the main one. And again, you know, we had to make sure that the ones that we were looking at billions of years ago were behaving in the same way. And we did that by looking at a collection of them at the same redshift. And we found that, yeah, indeed, the more luminous ones, the brighter appearing ones, had slower rise and decay times than the less luminous ones. And so, and the spectra of the type 1As look the same, and other aspects of the type 1As look the same. And so we had to gradually build this confidence that we really are looking at the same kind of light bulb, not a bicycle light or a big semi-truck light or anything like that. So I thought I'd
Right.
just mention that
No, it's really
because
important.
that's really an important point. Yeah.
And it does raise a quick side question of direct relevance. So I gather what you're saying is that observers notice this pattern in the light curves
Yes.
correlating in the steepness and the ultimate brightness. Do we have a theoretical understanding of this now, or is it still the
Yeah.
pattern in the
More or less, I would say, right? You know, in science, of course, we never know everything, and we keep on improving our knowledge and testing hypotheses. But the basic idea is that in this thermonuclear runaway, essentially an uncontrolled nuclear fusion reaction set, compared with our sun, which is a very controlled fusion reactor. It's what we want to build here on Earth to solve our energy crisis, right? But it's hard to confine the plasma. The sun does it through gravity. But in the white dwarf, you have an uncontrolled set of nuclear reactions, because when you have one nuclear reaction, that then generates energy, and it gives that energy to the nearby nuclei. But being this weird degenerate matter, it doesn't respond by expanding when it gets heated. The degenerate matter doesn't really respond to temperature differences much. And so that energy goes into moving the particles more quickly. And so that creates a nuclear reaction among them, and that gives more energy to their neighbors. And so you get a thermonuclear runaway. And a whole bunch of radioactive nickel gets produced. It's kind of interesting, actually. but it's because it's some number of helium nuclei, and carbon and oxygen are 3 helium nuclei and 4 helium nuclei, and I guess 16 helium nuclei. 16 times 4 is 56, and indeed, you make an isotope, a radioactive isotope of nickel, by fusing lots of carbons and oxygens together, and that nickel then decays, and that's what causes the optical visible brightness of a type 1a supernova. Most of the energy of the explosion got used up in expanding the star and making it big. So we see the type 1a supernova glowing for weeks or months because of the decay of these radioactive elements, primarily nickel. And it turns out that depending on exactly the mass of the white dwarf that explodes, they're not all exactly at the same mass, and depending on the chemical composition of the pollutants within the carbon-oxygen white dwarf and other factors, more or less of this nickel can be produced. And so that heats the gases of the exploding white dwarf to a greater or lesser amount. That changes the opacity or the transparency of those gases, trapping the energy of the radioactive decay, which comes out in these high energy photons called gamma rays. It traps them to a greater or lesser degree, and that then affects the luminosity of the observed type 1a supernova. But exactly which kinds of white dwarfs explode with what amount of nickel produced and all those details are not super well understood yet. And so we're still trying to learn those details.
Yep.
But at least
And
empirically, observationally, we can see that the relationship that we determine with the nearby ones applies to the distant ones. So I personally, though I would like to have a better understanding of the theory and all that, I'm not super bothered by our still incomplete knowledge of precisely what's going on, because we can empirically see that these things are good standardizable candles.
so, as a theorist sitting a few megaparsecs
Yeah.
outside the details of what you're describing, it strikes me, and I guess this is incorrect, but it strikes me that there could be 5 or 10% wiggle room in all the details of all the different kinds of very specific configurations of a given supernova that could account for small variations that collectively would yield a 5 or 10%
Mm,
difference in the final result. But that's wrong. You want to say to me, that's
okay.
just not the right intuition.
Well, you've brought up exactly the right point, Brian, and that's what people were saying when they thought that, well, okay, you're using type 1a supernovae. It's a tried and true technique. You discovered the accelerating expansion of the universe, but now you've got to make the measurements and their interpretation ever more precisely, ever more accurately. How do you know you're right? Okay. So this is where verification through completely independent techniques becomes so important. And that's true in all of science. But the more important, the more impactful your discovery, the greater is the onus of verifying it with completely different techniques. And we can get into those techniques more later on if you want. But for now, it suffices to say that other techniques that are completely independent of type 1a supernovae that try to measure this current value of the Hubble constant get the same value that we do, but with a greater uncertainty, a greater error bar right now. But there are 5 or 6 or 7 such techniques right now, and they're all giving about the same answer with slightly bigger or significantly bigger error bars. But when you put them all together, collectively, they give the same error bar or nearly the same error bar that we have and the same answer. So all of the nearby universe measurements, with the possible exception of one, which I know you'll want to talk about, give the same 73 kilometers per second per megaparsec. And that gives us significant confidence that our technique of focusing on the type 1As which we still think is the best technique in terms of its error bars, is giving the right answer.
Got it. Got it. So I do want to talk about those other measurements, but let's not do them
Right.
immediately. If
Yeah.
it's okay, let's come back to them. So, but you did mention error bar, which I think is a vital one. So for your measurement of 73, is that your central value?
Yes.
73?
Mhm.
Yeah. So what is the error bar
Right
that you're
now, we're
finding?
down to 0.9 kilometers per second per megaparsec. And I
Okay.
think the number is, it's 73.2 if you want three significant digits, 73.2 plus or minus zero point 0.9.
Right.
Yeah.
So 72 in change to high 73s or something
Yeah,
like
at
that.
one
Is
standard
right.
deviation. But the point is,
Yeah.
you'd need to go to more than 5 sigma, 5
To
times zero
overlap.
point 0.9, to bring you down to the 67 or 67.4, more precisely, plus
Yeah.
or minus zero point 0.6 or so, that I think
Yeah.
that the cosmic microwave background radiation people are
Yeah.
saying. And
So let's
that's the
turn let's
tension.
turn to that. If let's turn to that if that's and we can drill down at whatever level of detail you feel so moved. But maybe it can bring up the Planck CMB
Sure.
graph that we can sort of see that. And so in the other camp, if you will, the
Right.
other approach to coming to a value for the expansion rate starts with this picture and a theoretical model. So you can just give us a thumbnail sketch of how they
Yeah.
use this and theory to get to a value for the Hubble
Right.
parameter.
So this is magnificent. This is a thing of beauty. My jaw dropped when I saw this from the Planck mission. And prior to that, there was a thing called WMAP that showed all these freckles. And prior to that, there were some measurements that showed an even more fuzzy view. What we're looking at is an infant picture of the universe when it was, we think, about 380,000 years old. And we're looking at basically the temperature of the whole sky. This funny little oval is the whole sky. And to a first approximation, in fact, the temperature is 3 degrees above absolute zero everywhere. Indeed, 2.725 plus or minus zero point 0.001 or something like that. But if you really dig deep and you subtract out the 2.725, you find at a level of a few parts per 100,000 up to about 1 part per 10,000, so 0.0001, slight differences in temperature, and the hotter regions are shown here as orange or yellow or red, and the colder regions are shown as blue. Uh, and these correspond to slight differences in the density, the mass per unit volume of the gas in the early universe. And you can think of this as, when you're pumping up a bicycle tire, it gets hot, right? Because you've done work on it, you've pressured the gas, and you've made it hotter. So the denser regions, at least on small scales, appear hotter. And then on large scales, some of these bigger blue or orange red regions, they appear slightly different temperatures for other physical reasons. But the point is, there are various physical reasons that give rise to these tiny little temperature variations, or freckles, as I like to call them. And they are of utmost importance to the universe and to us, because it is from these tiny density variations that we can talk about later how they were imprinted there. But it's from these tiny density variations that gravity, that great sculptor of the universe, was able to create galaxies and clusters of galaxies containing stars, because the denser regions would gravitationally contract and they would steal material from the less dense regions. And so you'd get these voids and clusters of galaxies. And here we are, nearly 14 billion years later, discussing this.
Yeah.
But the point is that the size of the typical freckles, and you can see there's some big ones and some small ones, but looking at this map, there's a typical size, and it turns out to be about twice the apparent size of the full moon, 1 degree in the sky. And you can see them. Your eye sort of sees that there are all these ones that are about the same size. It turns out that those are the most frequent size because those are the most frequent size of the density variations that had grown by an age of 380,000 years. And the density variations to which those correspond were sound waves, pressure waves, traveling through the early universe. And they reached a certain size by 380,000 years, beyond which time they stopped growing for reasons we can discuss or whatever. But the point is that largely independent of what the universe has been doing since that time, the early universe behaved the same way shortly after the Big Bang, regardless of how much matter it has now and what its density is and what its future will be and all that. It grew in about the same way, regardless of all those details, in the first 380,000 years. And so physicists can compute the expected physical size of these typical density variations. And we know how far away they are. They're about 14 billion years in time. So we can predict first we can use them to tell that the universe overall is what we call flat. It's dictated by Euclidean geometry. The sum of the interior angles of a triangle is 180 degrees. And that's very interesting because that implies that the overall density of the universe is near some critical density. But beyond that, we can see these freckles, and we know their size at 380,000 years. And we can then essentially use the standard model of cosmology to predict what the current expansion rate should be, using those measurements and then using the standard model. And that's where the prediction is 67.4 kilometers per second per megaparsec. And then there's something else we can talk about later where, again, you can use these fluctuations and predict how they will grow in size. And we can see their growth in the distribution of galaxies. Those are called baryon acoustic oscillations, but we can talk about them later. And that's another way of using the early universe data to predict what the current Hubble constant is. And all of the techniques that are somehow linked to this map of the early universe give the smaller value of the Hubble constant with a very small uncertainty. And that's the tension.
And how much is the uncertainty now? Do you have off the top
Yeah,
of the head?
I think they said 67.4 plus or minus 0.6. But remember, those are statistical uncertainties. You have to worry about what potential systematic effects have they not taken into account. And I'm not an expert on the cosmic microwave background, but there are a lot of smart colleagues of mine here at Berkeley and elsewhere who work on that. And they think they've got things under control. Moreover, there are these other techniques related to the growth, the continued growth of this structure in the universe that also suggest 67 or 68 or 66 in some cases. And so they all suggest this smaller value. And that to me implies, or at least suggests, that there's either something wrong in the standard model going from 380,000 years to now, or what could be happening is that their predicted size, physical size for these little freckles is wrong. And that could have been the case if there were something affecting the early expansion of the universe. After the so-called inflationary phase, which made the universe really big, but before this microwave background radiation was released. And I didn't mention, but I should add that that radiation got released when electrons first combined with protons to form neutral hydrogen in the universe. Because prior to that time, the universe was a plasma. It was an ionized gas, and the electrons scatter light really well. And so you can't see an object that's over there. The light won't reach you in a direct path. It's kind of like if you filter the sun with a proper filter, you're looking at a solar eclipse or something. You can't see through the sun because it's a plasma, it's an ionized
Right.
gas. So if something affected the expansion rate of the universe prior to this time of recombination, it's called, when the electrons combined for the first time with the protons to form a neutral gas through which light could travel. If something affected the expansion prior to that time, then the calculation of how big the expected physical size would be wrong. And that would mean that the assumption that the cosmic microwave background astronomers are using in their extrapolation would be wrong. So it's not anything wrong that they did in applying
Sure.
their model. It's that their initial conditions, their assumptions were wrong because of something we did not previously know. And that
Which
would
is
be really
dramatic.
exciting as well, right?
Yeah. So I think the main point then is if this is a true discrepancy between the two numbers, to bring them into concert, one would have to change our understanding of the basic processes that happened in the early phase of the universe or, something later as well. I'm sure there are many creative people who put forward
Very
ideas that,
exciting, though.
yeah,
You know,
very exciting ideas.
any of
Exactly.
those things, either the early
Right.
universe or subsequent to the release of the CMB, the cosmic
Right.
microwave background radiation, would be something we did not know already. And so an important modification to the standard model. It would not negate the idea of the Big Bang.
Right.
Indeed, some of the James Webb images of early formed galaxies are very, very interesting. They mean that our models of galaxy formation and evolution might be wrong. And that's very, very interesting. But that does not negate the standard idea that the universe began hot, dense, and expanding for whatever
Yeah.
reason. But the details would change. And, we're trying to understand the details better and better, right?
Yeah. Yeah. No, huge. And so this does lead us then to those measurements that you obliquely made reference to a little while ago,
Yeah,
because
let's do that.
I had a conversation of this sort with Wendy Freedman some months
I
ago.
watched
And
it.
oh, you did?
Yes.
Okay. And I think as many people who watch these kinds of programs know, Wendy Freedman has been a dominant figure in the issue of trying to measure
Yep.
the Hubble
Yep.
parameter over
Yep.
the course of many decades, has been a central figure in all that. And as you may recall in that conversation, Wendy basically came to the conclusion that the current measurements, the measurements of the Hubble parameter today, were migrating closer to the CMB, and the overlap between them was sufficiently large that she no longer considered it something that was really anomalous. And so these wonderful hints that maybe we have to change our understanding of the early universe or our cosmological models or the things that you just made reference to, her point of view was it's not going to come to that. So where do you come down
Right.
on her
Yeah, yeah.
perspective?
So first of all, let me start by saying I have great respect for Wendy. She's been a leader over the decades in lots of astronomical studies, but in particular, in the early days of the Hubble Space Telescope, she led the so-called key project where they wanted to measure Cepheids in galaxies that had hosted Type 1a supernovae. So she's quite well versed in these types of studies. It's just that back then they reached too few galaxies that had hosted Type 1a supernovae, and the measurement techniques weren't as good as they are now. Hubble is now more than 30 years old, and so we've done better. But she started those measurements. Uh, Her latest work, however, conflicts with ours. She gets 70 kilometers per second per megaparsec and with a bigger uncertainty, thus decreasing the tension for two reasons. As you said, her value is 70, not 73, and that's closer to 67. And her uncertainties are bigger, and so that makes for a bigger overlap, decreasing the tension. So there are two main issues as I've seen them. And we discussed those issues in a paper with Adam Rees and a team of people that commented on at least the first version of Wendy's recent paper. And the first obvious thing is that with James Webb Space Telescope, she has so far measured only about 10 of the 42 galaxies that we measured. So it's a smaller sample. So just small number statistics give a bigger uncertainty. So that leads to less tension, it leads to more overlap with the CMB measurement because the error bars are bigger. So that's sort of a trivial reason that the tension has decreased. But to think that the sample of 10 is somehow a better sample than the sample of 42 we have is incorrect, because Adam has shown with James Webb images that, in fact, for the sample, the subset of galaxies that we measured with Hubble, that subset measured with James Webb gives actually the same distances to the galaxies that we had gotten with Hubble. So our method of getting distances is correct. And Wendy's distances for those galaxies are the same as ours. All right. But we have 42 galaxies measured that way rather than 10. So why not use the full sample, right? There's no reason not to use the other 32, given
But
that
just so I can understand fully, if you restrict it to the 10 that she's
right.
focusing on, would you get her answer?
Wait a minute. That's the second part that I'll get
Okay,
to.
I'm sorry.
Okay.
Yeah,
But
yeah,
what I'm first just saying that if I restrict attention to just the 10 that she measured,
yeah,
using Cepheid variables, and there's a few other techniques, tip of the red giant branch and whatever,
yeah.
we agree on the distances for
Okay.
those 10. So that means we're getting the distances correctly with Hubble. And then that means why not use the full set of 42, right? You see what I'm saying there?
Sure.
In other
Yeah.
words, the criticism that we might have gotten the wrong distances because of crowding in the images with the Hubble, which aren't as clear as the images with Webb, that's no longer a fair criticism, because the Webb images without crowding of 10 galaxies that have been imaged with Webb so far give the same answer as our Hubble images. And with time, we're getting more and more Webb images. And so we'll be able to directly test this for all 42. But the
Mm.
point is, for the 10 that she chose, we agree on the distances. For a while, there was a difference. I think tip of the red giant branch still, which is a technicality, we can discuss it or not discuss it depending on how much time you have. But for a while, it was giving significantly different and lower distances. Now I think it's about the same, maybe a little bit on the low side, but with bigger error bars, because it's a more difficult technique to use than type 1a supernovae. But she and we largely agree on the distances to those 10 galaxies. So the distances are not in error, and so we might as well use the whole sample. Why not? We've got the correct distances. That use of the whole sample decreases our error bars to only 0.9 rather than 2 or whatever kilometers per second per megaparsec. Okay.
And there's no reason to suspect that the other 32 might somehow differ between Hubble and Webb.
No,
There's nothing that
no.
suggests
And in
anything
fact,
like
I think in the time since the first version of her paper, or in the time since Adam Rees wrote the James W. James Webb Space Telescope paper showing the relationships that are found, the period luminosity relationship, blah, 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 they are statistically indistinguishable from what we determined with Hubble. So there's no reason to doubt the distances to the 42 galaxies. But then we get to the second thing that you were hinting at. Okay. All right. All right. Out of the 42 objects that we measured, Wendy had a subset of 10. Now, it turns out that we can calculate on a galaxy by galaxy basis for each of these 42. Suppose it were the only galaxy and the only type 1a supernova in the universe. What would the Hubble constant be? V, speed of recession, equals the Hubble constant times the distance. We measured the distance with the type 1a supernova. I'm sorry, we measured the distance with the Cepheid variable, and then, we get the Hubble relationship, basically. And we calibrate the true power of the type 1a supernovae, and we tie that into the ones that are a couple of 100 million light years away, the thing we discussed before. But anyway, suppose we only have one calibrator, all right? You get a Hubble constant from that one calibrator, and it's some value, and it might be 73. But then we use another one, and it might be 74 and a half. And then we use another one, and it might be 72 and a half. And another one, it might be 71 and a half. And then a fifth one, and it might be 73.1. You get a distribution of values because, any scientific measurement is going to have uncertainties. And there might be even some systematic thing we didn't quite take into account when looking at some Cepheid or whatever. But you can plot the number of supernovae versus the value of the Hubble constant that they give, and you get a distribution that looks like this, that peaks at 73.2, which is our number, all right? But some are on the high side, 74, even 75. One might even be at 75 and a half or 76, I don't remember. But some are on the low side, 71 and a half. Or 72, 71 and a half, 71, even 70 at the low end of the distribution. Wendy's 10 galaxies are all systematically at the tail end of our distribution. If we choose only those 10, we get 70 kilometers per second per megaparsec. We don't disagree with Wendy. She had the bad luck, the misfortune of choosing 10 galaxies that were all at the low end of our distribution. Okay? Indeed, there's only a chance in 1,000 that happened at random. You take 10 galaxies out of a distribution of 42 and stuff, and she was just unlucky. She, I think, recognizes this issue at this point, and there's a new version of the paper that has either come out, and I haven't read it yet, or because I've been busy teaching this class of 800 students, or it's about to come out or something. I've heard from other colleagues that either there's this paper, I should have read it, I'm sorry, I was just too busy this week, but I've heard either from conferences or a preliminary version that one of my colleagues saw of that paper that indeed their tune has changed to some degree in the direction that our rebuttal paper, if you can call it that we wrote after her paper first came out on the archive. And it was the subject of much discussion. And you even interviewed her because people start saying, there's not a Hubble tension and the universe isn't trying to tell us something interesting because here's this very good group of researchers that are getting a value of 70 plus or minus 2 or whatever it was, not in direct conflict with 67.4 plus or minus 0.6. But we think that it was mostly a combination of those two things. The bigger error bars and statistically it being very unlikely, but nevertheless a fact, that their 10 objects were at the low end of our distribution. So as she measures more and more of our galaxies, I'll bet she'll find a bigger and bigger Hubble constant.
And is your 42 pretty much the data set you're going to stick with, or are there capacities to expand that even further?
It's hard, Brian, because with the Hubble and the techniques that we've perfected, it's really hard to measure Cepheids in galaxies that are at greater distances. And you need to have significantly greater distances in order to double the sample of type 1a supernovae, because if you only add 3 or 4 to 42, that's not really a substantial increase. When you get to samples of this size, typically people say, well, you have to double the sample, and then the statistical errors go down by the square root of 2. All right. And so that's 1.4, and that becomes kind of significant. Now, with the Webb, there are efforts to go out to more distant galaxies, but it's a slow process. It took us 20 years to get enough time on Hubble to measure the distances of 42 galaxies with Cepheids that had hosted type 1a supernovae. And that's because there are lots of other interesting astronomy projects to do. And so people interested in exoplanets or the evolution of galaxies or whatever, they might say, well, we don't want to give you that much time. And actually, the evolution of galaxies people, we can kind of work with them a little bit because they need long exposures on galaxies, and they can separate those exposures into a whole bunch of different visits with the James Webb. And each of those visits then might reveal a type 1a supernova, But it's not those supernovae in the earliest galaxies. We need ones in relatively nearby galaxies, and those aren't particularly faint. And so people studying relatively nearby galaxies only need 1 or 2 pictures. And so it's harder to work in concert with them, right? So it's going to be a long slog. And we're trying to look for other methods for getting accurately the Hubble constant. And there are other methods that may yield results on a shorter time scale than the type 1a supernovae. And so working on that, there's, gravitational lensing, and there's a technique called surface brightness fluctuations, and yada, yada, yada. So it's a very interesting problem. So we are working on it, but it's not going to be, overnight results or anything like that.
Yeah. So assuming this holds up, do you have a gut feeling on explanations that you've encountered so
Oh,
far for
yeah,
what is likely? You already made some reference
right.
earlier to new physics between the Big Bang and 380,000 years, time of
Yeah.
decoupling. But is that the explanation that strikes you as the most promising, or have you seen other more exotic things
Yeah.
that have caught
Yeah,
your
it's a
attention?
great question, Brian. I should ask you because you're a theorist, I'm an
Yeah.
I'm an observer. I like to joke that
Well, look,
I
I love the idea of a new
yeah,
phase of distinct
right.
expansion between, that
Yeah.
would be
Yeah, yeah.
wonderful,
So
if that's
so
the way
I
it
know
turns
which
out.
end of the telescope to look through. So what I'm about to say will be things that my theoretical colleagues tell me. But here's one idea, and that is that if there was, for example, an early burst of dark energy, similar to but earlier than the phase we are now experiencing over the past 4 or 5 billion years, where the repulsive component of the universe started dominating over the attractive component. So you went from slowing down. Actually, I have an apple here, right? When there's normal gravity acting upon it, it slows down. But if there's this repulsive anti gravity, if you will, or the dark energy, the cosmological constant, whatever, then eventually, as the universe's density decreased enough, but its size increased such that the cumulative effect of the repulsive stuff dominated, then it started accelerating. Well, if there was a similar component of repulsion after inflation, which we can or don't necessarily need to talk about, depends on your choice, but prior to 380,000 years, probably reasonably early in the universe, but later than the first tiny blink of an eye, which is when inflation occurred, then that would have caused an extra expansion at early times, an extra cooling of the universe. And so the electrons would have come together with the protons at an earlier stage, because they do that at a temperature of around 3,000 degrees above absolute zero, 3,000 Kelvin. And that would have been reached at an earlier time. So that would have meant that sound waves didn't have as much time to travel, and they wouldn't have formed such a large physical structure at the time of, recombination. So then the assumed structure that the CMB people and the baryon acoustic oscillation people use would have been wrong, and so that would have affected their calculation of what the Hubble constant should be. And to give perhaps a simpler but not entirely correct visualization for the typical listener, it's like you're watching a kid's soccer game and you're kind of myopic. You're only looking in one direction and you see the soccer ball zipping by faster than any one kid could have kicked it. Well, what if another kid kicked it in the same direction earlier, right? Then it would be going faster. But it's a bit more subtle than that because it affects this, what we call the sound horizon, the distance that a sound wave could have traveled in those early few 100,000 years of the universe. And that then affects the calculation of what its size would be now, and so on and so forth.
Yeah, yeah. No, I find those explanations certainly pique the
Yeah.
imagination.
And
You know,
another one
and
that's similar to that in overall character is that the early expansion rate of the universe, when you look at the equations, depends on the composition of the universe. And in particular, it depends on how many relativistic particles there are. Those are particles that move at speeds close to, but slightly less than the speed of light. And neutrinos, these funny little particles that travel through a light year of lead without being scattered. I mean, half of them could travel through a light year of lead. So it's as though it were a vacuum. They're produced by exploding stars and by our sun and stuff like that. If there were additional flavors or types of neutrinos in the early universe, that could affect the early expansion rate as well. The trouble is, the neutrinos are associated with how many families of particles there were or are in the universe, and that affects the degree to which hydrogen and helium and their isotopes being the same number of protons but different numbers of neutrons, that affects how many, and the relative abundances of these various isotopes that were formed. And we think we know that pretty well. And so if there are other types of neutrinos, they have to be what are called sterile neutrinos. They don't participate in what's called Big Bang or primordial nucleosynthesis. And there are other problems then. And each of the proposed explanations, including the early dark energy that I mentioned, has other problems and is not a fully accepted or verified explanation for what's going on. And then there are explanations post or after the CMB formation, and we can talk about those if you want.
yeah. So I would like to move on from here, but I think the quick summary that I think is worth just quickly emphasizing is the very fact that there are two radically different ways of coming to a measurement of the Hubble parameter, using early universe measurements, using more late universe, current measurements, and that they are within such a shouting distance of each other is a tremendous, huge accomplishment in its own right. And then the fact that you, and I'm going to put myself in this group just as the science community, the fact that the science community can, with a straight face, talk about, a 10% difference between two measurements of the expansion rate of space and take that seriously because of the refinement of the measuring techniques, and perhaps use that to point toward new physics that we've yet to find, is just utterly astounding. I think that's part of the message that
Oh,
anyone should
yeah.
take away from this.
Brian,
You know,
45
yeah.
years ago when I was beginning graduate school, there was this big debate. Is the Hubble constant 50 kilometers per second per megaparsec
Or
or
100.
100? And by the way, to a good first approximation, the age of the universe is the reciprocal of the Hubble constant. And that may seem weird, but it's kilometers per second per megaparsec. Kilometers and megaparsec are both units of distance, so they cancel out when you do the unit conversion. You're left with inverse seconds. And so, in fact, if you flip that over, you can show that that is a pretty good approximation to the age of the universe. So what that meant was we didn't know the age of the universe to better than a factor of 2. And here we are discussing 5 or 10%, right? It's astonishing progress indeed, largely with the type 1a supernovae and the measurements of the cosmic microwave background radiation. Cosmology has become a precision science. right? We used to be joked about by other physicists, that, well, you guys, you're not making very precise measurements. You don't even know the age of the universe, and we've come a long way, so that's fantastic.
Yeah, I think part of the joke in the old days was the error bars were in the
Yeah,
exponent,
yeah,
you know?
yeah. Maybe not quite that bad, but
Yeah,
yeah,
right.
yeah,
Yeah, that's been an
yeah,
exaggeration, no doubt. But talking about the age of the universe and the early stages of the universe, inflationary cosmology, which you've mentioned a couple of times, has been a dominant paradigm really for call it 40-ish years, something like that. In recent years, there have been more serious challenges that people have put forward. And, famously, Paul Steinhardt, one of the people responsible for the earliest successful models of inflation, has radically changed his perspective and is now really developing other approaches, cyclic models of the universe. Roger Penrose, somewhat of an outlier, I would say, in cosmological discussions, but look, the guy won the Nobel Prize. He's a extremely smart person, so we really need to take seriously things that he talks about. Doesn't mean that they're right by any means, but I had an interesting conversation in a forum much like this months ago, where he went into some detail on the conformal cyclic ideas, which I hadn't really studied in much detail until that conversation, but they're certainly interesting. Neil Turok, has versions where you have sort of a mirror symmetric Big Bang and sort of a Big Bang going the opposite direction before time zero. So there are all these things that are on the table. So where do you stand on inflation? I guess even the more precise question is, do you consider inflation a falsifiable theory?
yeah. Wow, there's a lot to unpack there, Brian. First, I do like inflation. It does resolve some apparent inconsistencies in the standard Big Bang model, where you have to assume the universe was uniform in temperature and density at very early times. And there's no physical reason for that unless you invoke inflation. And you have to assume that its density was tuned to a very precise value, because had it been slightly more or slightly less, it wouldn't be near this very special value that we measure now, which in some units is 1.0. And then there are issues in particle physics, magnetic monopoles. And then the distribution of those freckles in that Planck map, the relative amounts of these different fluctuations, that's explained. And then the flatness, the idea that we see a flat universe, and we actually have indirect evidence that extends beyond what we can actually see. There are details in the microwave background. There's a lot of things that it's pretty good at. And
Yeah.
so that sounds good to me. However, inflation is too malleable. There are too many tuning parameters, that little bells and whistles that you can fix up. And indeed, decades ago, before we knew about the dark energy that makes the density equal to 1.0, it was zero point 0.3 before that, if you only counted visible matter and dark matter. I remember conversations with Andre Linde at Stanford, who is one of the other main originators of inflation. And he said, well, he's got a model of inflation that has a density parameter of 0.3, not 1.0. And I'm all, Andre, one of the great aspects of inflation was that it predicted 1.0 and a flat universe and all that. And he said, yeah, but I've got models of inflation that aren't 1.0. And that was a symptom of a bigger issue that, and I think it's one of Paul Steinhardt's main criticisms, that it's sort of almost infinitely malleable and not falsifiable. No matter what we find, you could have a form of inflation that is largely consistent with that. And so that is an issue with inflation, and it makes it not entirely falsifiable, maybe not even at all falsifiable, but it may still be true. So it's a little bit like the multiverse. I'm a big multiverse proponent for a number of reasons, and there are different types of multiverses. But that's not a falsifiable conjecture either. And yet, it's not that we wake up at 3 in the morning to go to the bathroom or something and say, oh, let there be a multiple universe, or oh, let there be inflation. There are good physics reasons having to do with, quantum mechanics and general relativity for, as you know, both thinking that there's a multiverse and for thinking that there may well be inflation. And it may be that those things are true, even if they're not falsifiable. And so they are on the boundary of what you could call science, and in particular physics. And if you were Karl Popper and take a very strict definition of what science and physics are, it's got to be a falsifiable hypothesis. But there are many definitions of science, and you can be more or less strict or conservative. And I tend to be in the camp where, as long as you used good physics to come up with a potential new interesting idea, that idea doesn't necessarily have to be falsifiable, at least not now, right? Maybe someday it will be falsifiable. Some young whippersnapper, maybe among my students, will find a way to test for these things. And so I'm a little bit more lenient in what I call science, but I do acknowledge that inflation has that very valid criticism. Having said that, I'm not sure that Steinhardt's or Penrose's ideas are any better. I mean, just very, very briefly, Steinhardt has this ekpyrotic or cyclic version of the universe where he starts out with these gigantic, maybe infinite parallel branes like membranes, and they collide. And when they collide, you get a hot Big Bang, and they pass through each other and they can collide again. And so you get many Big Bangs. Well, I've had this conversation with Linde. You have to start out with these parallel branes that are really big. It sounds to me like inflation might even produce those branes, right? You need some initial assumptions for him. And then for Penrose, he's claiming that he sees evidence of the previous universe in terms of patterns in the microwave background. And this is a way, by the way, that we know that the universe is at least significantly bigger than what we see by a factor of at least 100 in volume. And that is that if it were much smaller, there would be paths that photons could take along different directions of this sphere or hypersphere, if you will. And you would see matched patterns. In an ideal case, you get these matched circles, okay? And Penrose has a similar sort of a correlation from information coming from some previous cycle of the universe. And he says that he has observational friends who have analyzed the CMB map and see variations of this sort, but others haven't seen them, or at best see them at a level where there's a 5% chance that you would see them in a universe that you happen to be in, right? It's a little bit like one of those big cold blobs in the map. It's pretty cold and it's pretty big, and it's actually statistically a bit unlikely, but in 5% of universes that we happen to find ourselves in, there would be such a cold spot. That's 2 standard deviations. Most of us are not willing to say that we're seeing evidence from previous incarnations of the universe before our Big Bang, just based on something that has a 5% of chance of being a statistical fluke, right? So
Yeah.
I find those things to be, and their ideas to be less persuasive than inflation, and with fewer observational consequences that have been verified, like flatness and homogeneity and isotropy, that is, uniformity of the universe, and absence of magnetic monopoles, and explanation of the distribution, the so-called power spectrum of this cosmic microwave background map,
Yeah. Yeah. No, I tend to take a very similar view as yours. Sometimes an argument is made, and sometimes I've made this argument really as devil's advocate more than anything else. Take the standard model of particle physics. It also has, in principle, a lot of parameters in there. Many of them we set to zero because we don't need them. But if you wrote down, again, just to be in technical language for those in our audience who speak this language, if you wrote down the Lagrangian of an effective field theory that included the standard model, it could have a whole bunch of other terms that in principle, if you needed them, you could adjust them to match data, or you can include other features as well. And so you could say that the standard model, or really I should say quantum field theory, is kind of unfalsifiable in the same way, because you could do what Linde did to inflation, adjust the theory to get something that perhaps some experimenter unexpectedly had found. But the point that I think many have made in these conversations is we scientists, astronomers, physicists also have a sense of economy and a sense of elegance. And if you have to continually add epicycles metaphorically to a given framework, if you have to take the original idea of inflation and then start to add features to it to match the data, it just becomes less convincing. If we had to do that in the standard model, it would have become less convincing. But the bread and butter, most straightforward versions of the equations do a pretty good job. And so far, inflation hasn't had to stand on its head to
Yeah.
match data, but who knows, maybe at some point it will, and then it would become just
Yeah.
not wrong, but less
Right, right.
convincing.
But I also just thought of something, and that is that some aspects of inflation in some ways are falsifiable, or at least you can distinguish between, say, Steinhardt's ekpyrotic model and inflation. And let me mention
In terms
this.
of primordial
The
gravitational waves.
primordial gravitational waves. Okay,
Yeah,
this is very interesting.
yeah,
So there were little
yeah.
quantum fluctuations in the early universe in the density and stuff, and then inflation made them really big. And those variations in density led to little ripples in the fabric of space time, the title of one of your books, right? So and those ripples are bigger in most inflationary cosmologies than they are excuse me, in Steinhardt's model. Okay, it's not that his is completely inconsistent with primordial gravitational waves, but they're smaller, less easy to see, and so on. So though we can't go back physically to that time, and moreover, the gravitational waves themselves are really hard to detect. Indeed, it was amazing that nearly 10 years ago now, the first ones were detected from colliding black holes, which had 30 or so solar masses of material, and only a billion light years away, not 14 billion light years away. But little tiny ones, we may never detect them directly. But nevertheless, they affected the distribution of matter at early times and where, the protons and electrons were. And that then imprints a signal on the cosmic microwave background radiation. The scattering process causes what we call polarization. It's a little bit like light scattering or bouncing off of pavement or water is polarized, and it tends to have its electric field parallel to the surface. And so if your polarized sunglasses only allow the perpendicular component, which has been suppressed when it bounced off, then the glare from water or pavement or whatever goes way down. So that's an example of polarization. And in particular, if there were these gravitational waves, they would cause a type of signal where, if you look at a circle, instead of radial polarization this way and tangential that way, those are called the E modes after electric fields in a sense. You get ones that are at a 45-degree angle, sort of here, there, and those are called B mode polarizations. And that's something that could be measured in the CMB. And indeed, there are colleagues of mine who are working on this. In particular, in the Atacama Desert of Chile, there's this Simons Observatory, and they are trying to make this measurement. And there's a real hope that in the next years they will measure it. And they'll have to rule out other causes. Like, some years ago, there was a big announcement that, some signatures of inflation had been found, and turns out it was scattering by dust in our own galaxy. So that was a bit embarrassing. You have to worry about that. And then gravitational lensing, which is a bending of light by intermediate clusters of galaxies and things like that, can affect the rotation of the polarized signal. It can turn these radial and tangential things, if I'm not mistaken, into things that look like 45-degree angles. So there's going to be a lot of things they have to take care of, but there's the real potential of testing yet another aspect of inflation and ruling out at least most of the, as far as I know, Steinhardt models. And he could come back and say, oh, he has a way of having big gravitational waves, but that's tantamount to saying that he has some tunable parameters as well, right? So clever theoretical physicists can come up with ways of messing around with their original hypothesis, putting little band-aids
Yeah.
on it,
Yeah, I think many of the players today are of a mindset that if there is a detection of the B mode polarization indicating these primordial gravitational waves, I think many are, at least today, willing to say this would be significant evidence for inflation and significant evidence against the other competing proposals that are currently on the table. Now, two things: whether that would still be the mindset when these modes would be detected is an interesting question that nobody can answer now. But the other interesting question is, if they're not
Yeah.
detected, what do you do there? Because there are, again, models of inflation that can suppress the imprint. The B mode signature
Yeah.
can be much smaller, and so it
Yep.
doesn't rule out inflation, but again, it just makes it less convincing. I think many are willing to say that that would at least be evidence that these other approaches, have a real shot at being the better approach
Right. The
than
more we have
inflation
to
itself.
tune inflation to account for, let's say, only small or zero levels of polarization, the less
Yeah,
attractive it becomes. A little bit like my reaction to Andre Linde's early version of open
precisely. Yeah,
inflation, as it was called, or low density
yeah,
inflation. So,
yeah,
yeah, yeah.
exactly. So if we can turn final
Mhm.
topic, if you
Yeah,
still have the
sure.
patience to continue
Yeah,
the
yeah.
conversation, and thank you again, of course, for all the time you're giving
The
us.
pleasure.
You you famously were part of, at different times, both of the
Oh, yeah.
teams
Mhm.
that were responsible for detecting the accelerated expansion of the universe that most of us interpret as evidence for dark energy suffusing space. Can you just take us through a little bit of the history of that remarkable Nobel Prize winning discovery? So you were initially in the, I always forget the names of the
Supernova
two teams. So
Cosmology
actually, I'll let
Project.
you.
Yeah,
you-
Saul Perlmutter's
Yeah,
team.
yeah.
In a
Saul
project that was
Perlmutter's
actually
team. Yeah.
started by Rich Muller. He often doesn't get credit for having started that, but he gave it to his
Okay.
protege, Saul Perlmutter, who pursued it in a very fine way. Yeah, that was largely a bunch of physicists who came from high energy particle physics and stuff. Indeed, Gerson Goldhaber, who I believe was the first on Saul's team to realize that the Type 1a supernovae were fainter than expected, thus farther away, thus maybe propelled out there. He came from particle physics. He was quite an eminent particle physicist. And what they needed was an astronomer who knew about supernovae and had studied Type 1As and was a spectroscopist, which is what I'm trained to do, and has access and has used the biggest telescopes in the world, the Keck telescopes that are 10 meters in size in Hawaii, to take spectra of faint little dots that might be exploding stars and determine whether they are the right type of exploding star and make the measurement of the redshift and so on, and have a track record in applying for and getting time on big telescopes. So I sort of fit that bill in all the ways. I got interested in supernovae in 1985, where I accidentally discovered one that turned out to be a really interesting type. And so I started studying supernovae and then got interested in all the types. And I've been using big telescopes. And in particular, I would have had access to the Keck telescopes, and I'm a spectroscopist. So Saul recruited me onto his team. And then, meanwhile, Brian Schmidt's team started forming a little bit later, but it formed from more or less a bunch of astronomers and colleagues of mine and they wanted me to be on the team, but they said, I'm already in bed with Saul, so to speak, and so that would be a conflict of interest, and so that's the way it goes. Oh well, good luck. But over the years, as we conducted the projects, there are different cultures in science, and uh, Saul's team was more hierarchical, and that's not necessarily bad. It's just in high energy particle physics, you have these experiments with thousands of experimental physicists and engineers, and there's sort of one boss, and then there are underlings, and then there are the graduate students soldering circuits together and all that, right? Whereas with astronomers and Brian Schmidt's team, which was the high Z, the high redshift supernova search team, there were people who were experts in various things, but they talked with one another, and everyone was sort of equally important. And there was a nominal team leader, but everyone was sort of talking to each other about various issues that might be important. And on Saul's team, I kept bringing up things like, oh, well, what if there's dust? Or what if the type 1a supernovae 5 billion years ago were slightly different? In other words, various astronomical thorns in the side, if you will. And I had the impression that they wanted to sort of say, damn the torpedoes, full speed ahead. And there's something to be said for that attitude. But there's also something to be said for paying attention to the details early on, where you might alter the way in which you're gathering data or whatever. So to make a long story short, the culture was different from Brian Schmidt's team. And so at one point, Saul and I just decided to part ways. And I told Brian that I'm available now. And so he said, I'll get back to you tomorrow. And he consulted his team, and they all said yes, because they were colleagues and friends of mine, and I had access to Keck, and I knew a lot about supernovae and things like that. But I had done already enough of the observations for Saul's team in terms of verifying which of the little dots they found were type 1a supernovae and getting the redshifts and all that, that I would be a co-author on their paper. But I stopped being involved in the data analysis or knowing the results, because that would put me at an unfair advantage, and I could spill the beans, so to speak, to Brian Schmidt's team. So I stopped doing that. And I think I had a chance to read the penultimate version of his paper, but this is after Schmidt's paper was published by Rees, myself, and others. I was actually Adam Rees's postdoctoral advisor here at Berkeley. He was a Miller Fellow, which is a free agent, but I was his main advisor and mentor during that time. And that was a heady time. He would show me the results, and I would say, wow, these things look too faint. Are you sure you made the measurements properly? And then he said, well, Brian Schmidt made the measurements too. And anyway, it was a great time. But
Yeah.
yeah.
But
So
before you go on, there's one point that might be worth pointing out to the audience, which I remember I had a conversation with Saul around this time, and he emphasized to me something that was really enlightening, and it's exactly what you're describing, but sort of a different aspect of it. He said, look, we came from the particle physics. We come from the particle physics side. And in particle physics, Large Hadron Collider, whatever, big experimental undertakings, as you're mentioning, it's all about getting reams and reams of data. And within that huge data set, pulling out the signature of whatever, the Higgs boson, or, some kind of new particle, some anomaly of some sort. And he said that's what led him to think about doing these wide field images and doing, subtraction methods to find a large enough set of these supernovas to begin to do analysis on, how fast they're moving away. So would you say that, is that a good way of framing where the impetus came from, or would you say it's more in the air, even in the
yeah.
astronomical community as
So
well?
it's not, I understand the perspective he's coming from and what he described to you. And it was a particle physics type thing, and large data sets, and trying to find the needle in the haystack. There are hundreds of trillions of collisions in the Large Hadron Collider, and only occasionally a Higgs boson comes out, all that kind of stuff, right? But it's a little bit unfair, that characterization, I would say, because it doesn't give proper credit to people who had already used that technique to find supernovae. And in particular, I'm thinking of Fritz Zwicky, who at
Oh,
Palomar Observatory used an 18-inch Schmidt telescope, which is a wide angular field telescope, to look for supernovae. And it wasn't digital subtraction because these were photographic plates, okay? And we didn't
yeah.
have Moore's law back then, or at least it hadn't had many doubling times. But the technique of taking pictures 3 weeks apart and searching for what's new was not a
Mm.
technique that Saul's team invented. So there I would disagree.
So,
Yeah.
let me also jump in just for the audience. I'm going on a recollection of a conversation like 20 years ago or something. So Saul may have said
Ah,
something
okay.
much more, forgiving, from your perspective.
Yeah,
He may
maybe
have
he
given
gave
credit to
credit to
all.
Fritz Zwicky and stuff,
Yeah.
but
Yeah, exactly. So I don't wanna
yeah,
put words into his mouth. It was just interesting
right,
for me because it was a little bit of a light bulb in my own way of understanding because I hadn't really thought about this stuff before, and I was like, "Aha, that
right.
makes a lot of sense." But regardless of where the origin of
Yeah,
the idea came from. So then you switch teams, and can you take us through a little bit? I mean, you all, I gather, were anticipating that you would find that the expansion rate of the universe was slowing down over time because you have that
yeah.
apple right
Hmm.
next to you,
There you go.
and galaxies pull on galaxies, and that should slow the cosmic exodus over
Absolutely.
time. That's what and so when you began to see evidence from the supernovae and the speed of recession that wasn't the case, was this initially, oh, it must be wrong, let's go back I mean,
Yeah,
what was the
yeah.
thinking?
Well, as all good scientists, right, we're bred to be skeptics. And the greatest critics are skeptics of our own work because there's, of course, confirmation bias and all these kinds of things. But I would say there, the confirmation bias was sort of an inverse thing where people were saying, let's not publish this because it's obviously wrong, right? I remember Bob
Mm,
Kirshner, who had been the thesis advisor of both Adam Rees and Brian Schmidt, right? He was the PhD thesis advisor of both of those scientists. And then I became the postdoc advisor of Adam Rees. But he sent an email message saying, deep in your heart, or deep in our hearts, we know this must be wrong. And I had spent a lot of time, talking with Adam. And he had told me that he's not the only one making the measurements. He had told Brian the result, and Brian doubted it at first too. But that, this wasn't just something that they had come up with the previous day. And they were being very careful. And I had talked with them. And I said, Bob and others, what if we're right? And we should publish soon as long as we're confident that our statistical error bars have been done correctly and that we have at least tried to think about and remove potential systematic effects that might be affecting us, like the supernovae back then, 5 billion years ago, exploded with a different power. And there I looked at the spectra and they looked the same. And there were ways we could rule out at least normal dust because, like with the setting sun, it looks dimmer and redder because the blue wavelengths are scattered and absorbed more easily than the red ones. And we had gotten rid of that possible effect. And then there's stuff called gray dust, which are like bricks. Suppose there are bricks. They cut out all wavelengths of optical light equally. But there's a way of figuring out that there aren't bricks because it would increase the dispersion in our derived distances, blah, blah, blah. So we had done our due diligence. And I said, okay, look, we're only at the 95% or 97, whatever it was, statistical significance, 2.5 sigma. But we should present our results and make our data public and see what other people think about it. And so it was hard to convince the team to announce this prior to submission of a paper to a peer-reviewed journal. But I was scheduled to speak for the team at a meeting at UCLA organized around the search for dark matter. That was the big thing back then. And as you said,
yeah.
we anticipated finding that the density of the universe is 30% of what's needed and it's slowing down, but it'll never stop. So I was supposed to report on our progress, but we didn't anticipate any reasonably final and super exciting result. but I said we've got to talk about this, because a very good reporter, James Glantz, who had a PhD in physics from Princeton, he called me and others up, and he basically told me, Alex, I figured out what's going on by talking to enough of you and seeing an early graph that we had shown at a meeting in January 1998 of the American Astronomical Society. And so he could tell what's going on and that our error bars were getting small. So he said, Alex, if you don't announce this, I will. And I told my team, look, not my team, but Schmidt's team, that Jim Glantz has figured this out. And you can see from the data that the result is there. And so they said, okay, go ahead and announce it. And so it was fortunate that Saul and Gerson Goldhaber spoke first. And they basically had the result, but with bigger error bars. And so they said they're not very confident in it at all. And then I took a deep breath and spoke at this meeting. And I said, at the 95% confidence level, here's our result, and here are the systematic effects we've taken into account. And so go at it, everyone. Prove us wrong, right? And we then submitted the paper within 2 or 3 weeks. We submitted it in March. The meeting was in end of February. We submitted in March of 1998, and it was published by September of 1998. Not to take anything away from Saul's group, but they weren't quite finished with dotting the I's and crossing the T's. Their error bars still suggested a consistency with no acceleration. And they submitted in September of 98 and published in June of 1999. But we both had the result reasonably simultaneously. They just didn't have quite as good error bars at the time, So let's call it a
Right.
tie,
And so, yeah. And so, I mean, obviously, these are the moments that we all live for. Rare is the person who hopes to get that kind of a result that actually gets there. But there you were. I
It
mean,
was
what did that feel
amazing,
like?
and we each played a role, and I felt that I played an important role in confirming the Type 1a supernova candidates and getting their redshifts, and then talking with Adam quite a bit, although he was a real smart guy who did most of the analysis and the interpretation without any input from me. In fact, he came to my office one day basically and said, here is the result. And, my jaw dropped, and I told him, be sure to check it carefully. And he did. But it was just incredible. I mean, look, you know this, Brian, but let me say it for the public out there. It's unrealistic as an aspiring young kid who wants to be a scientist to think you're going to revolutionize our understanding of the universe, okay? The best you can reasonably hope for is to find something new and interesting that someone will later put together, like Newton or Einstein, into some tremendous breakthrough. But occasionally you're at the right place at the right time. And, we worked hard, but it was also darn lucky that I came across a supernova by accident, got interested in them, learned a lot about them, and was invited to become part of Saul's team and then Brian Schmidt's team. So I pinch myself, how lucky I was. But I also took advantage of an opportunity that fell in my lap, right? There was this supernova. It was weird. I was studying giant black holes and active galaxies at the time, but I branched off and, I continued studying black holes and things like that. But a big part of my research career started becoming supernovae, not for cosmological purposes, but because they are interesting things. They blow up and they produce the elements of which we are made. So I took advantage of that opportunity. And I tell youngsters, be on the lookout for opportunities and take advantage of at least some of them. You might not be in a position to take advantage of all of them, but be on the lookout and and work hard. And these kinds of successes sometimes fall in your lap. But never in my wildest dreams did I think that I would be part of something that so deeply revolutionized our understanding of the universe. Yeah.
Look, those are wonderful words of wisdom to end
Yeah.
our conversation on. And look, it's been a wonderful set of ideas that we've
Yeah.
spoken about, and many people will be waiting to see what does happen with the Hubble tension, and as further insights emerge, maybe we can have a follow-up
Yeah.
conversation and
Can I
sort of
mention
see
one thing? It
what
won't
that
take
takes.
long.
Please.
Because you
Yeah.
mentioned the Hubble tension and we just talked about the acceleration. we talked about
Yeah.
potential issues prior to the formation of the cosmic microwave background radiation. But other ideas are that subsequently, right, because the standard model is being used to make this prediction, and the standard model assumes that the repulsion is caused by an energy associated with space itself, a vacuum energy, Einstein's cosmological constant, although he didn't necessarily think of it in that way, okay, quantum fluctuations and stuff. If that's the case, then there's this discrepancy. But what if, for example, the dark energy is getting stronger with time? What if its density, the amount per unit volume, is increasing? That would cause an increase in the expansion rate. And though there hasn't been any definitive evidence for that so far, there are some intriguing little hints that are being made by various astronomers now.
That's a scary prospect too, right? It could
Well,
lead to the
that's
big
right.
rip in
If
the
the dark energy density is increasing with time, then although right now clusters of galaxies and galaxies are being held together by gravity, eventually the repulsion will rip apart clusters of galaxies, then planetary systems, then stars and planets and us, and even the atoms of which we are made. This is called the Great Rip. And, you know, it sounds like it violates energy conservation, and it does. But it turns out that in general relativity, you can, some of us think, violate energy conservation, and who knows. But and again, the evidence for this is not at all strong right now. But that could be one of the explanations. But right now, the data are more consistent with it being, an energy of the vacuum. But but maybe dark matter is interacting with light in some weird way to mess things up, or maybe there's some other explanation post formation of the cosmic microwave background radiation. So we're still trying to understand what the current acceleration is caused by. We've known about it now for a quarter of a century. But we've been working hard since then to explore the nature of this so-called dark energy.
Yeah, and just to tie this in with a conversation we didn't have too long ago with Daisy,
Yeah.
there's some evidence on the other side that maybe the dark energy could be weakening. It's too early to say. Is it weakening? Is it strengthening? Is it constant? But these are the wondrous
Yeah.
possibilities that await
I'm
further
looking forward to
investigation.
the
So
6-year data, or at least the 3-year data, which will
exactly,
be announced next
3 year.
March.
Yeah,
Their early
right,
discovery, which they have talked about, is based only on year one. And by their own
right.
admission, this is only tantalizing tentative evidence, which is only there at the 1, 2, or 3 sigma level, depending on which
Yeah,
auxiliary observations you include in the analysis.
right, right. Yeah. Yeah, and in any event, it's an exciting time in cosmology, Alex, and thanks so much for spending this time, and I look forward to further
Well, Brian,
conversations in
this
the
has been a
future.
true pleasure. I remember you once asked me to come to the Actual World Science Festival, and I had some conflict. I just couldn't come. And then it just hasn't worked out or something, but it's always been a dream of mine
Well,
to.
we will have you
Hey,
we'll have you in
let's
person
do
we will
that,
have you
okay?
in person for sure.
What a
Absolutely,
wonderful
absolutely.
conversation, Brian. Thank you
Fantastic.
so much for this honor and privilege.
Thanks. Talk
All
soon.
right, bye bye.
Bye.